Hi, I'm Fabio Di Mascia, a PhD student at Scuola Normale Superiore in Pisa, Italy, and in this presentation I'm going to show you my work regarding radiative transfer simulations of early supermassive black holes. Why early supermassive black holes? Because these objects, with estimated masses of around 10 to the 9 solar mass, power the bright quasars detected at redshift 6 and above, when the universe was only 1 gigayear old. It is very difficult to explain the presence of such massive objects in such short amount of time with the standard models for black hole formation and growth. And therefore, alternative models that allow for the formation of large seeds or that allow for super Eddington accretion are needed. But in order to constrain them, we need to find the progenitors of this supermassive black hole at redshift 6. How can we detect them? Motivated by the need for agent signature, we consider the cosmological simulations by Baran and collaborators 2018, in which a 10 to the 12 solar mass halo is followed from cosmological condition to redshift 6. These simulations carried with gadgets with standard prescription for stellar physics and an additional prescription for the black hole seeding and growth. We consider two runs of their simulations that are called agent sphere and agent cone. They differ for the way in which kinetic feedback from the black holes is implemented. In agent sphere, energy is injected onto the surrounding gas in a spherically symmetric fashion. In agent cone, it is distributed in a bicone. The evolution history of the black holes in the two simulations is also different because of the different feedback. In particular, in agent cone, black holes are more massive and accrete faster. At the end of the simulation, the most massive black hole in agent cone is has a mass 1 order of magnitude higher with respect to the most massive one in agent sphere. In order to obtain observational predictions for these objects, we perform radiative transfer calculations. We derive a dust distribution from the gas distribution by assuming a uniform dust-to-metal ratio. We adopt the dust model for the SMC, and we also consider the radiation from the AGN by setting the bolometric luminosity accordingly with the accretion rate predicted from the dynamical simulations. We obtain, for a particularly interesting snapshot, these results. On the left, you can see the UV emission for agent cone, and on the right, the infrared emission. We can see 4 bright sources in the infrared labeled with letters A, B, C, and D. 3 of these sources, A, B, and C, are galaxies that host a black hole at their center that is accreting. But we see that only one of them is visible in the UV, which is source A. Furthermore, the source corresponding to source C has the black hole that is accreting the most, but this black hole is completely dust obscured. And also the UV bright source is source A, while the far infrared bright source is source C. This system, that is an AGN merging system, will then appear as a quasar plus an SMG companion, which is something consistent with recent observations like the one by De Carlo and collaborators 2017. We can also be more quantitative by considering the spectral energy distribution of the 4 sources, here shown on the right-hand panel, in which source A, which corresponds to the red line, is brighter than the current deepest HST observation, and source C, the green line, is perfectly consistent with the Carli data. Therefore, this result is consistent with the HST and ALMA data. We then look for AGN signature also in agent sphere, which is a faint AGN. We compare the SED with a control simulation in which black holes were not seeded, which is called no AGN. And we consider the infrared and mid-infrared flux. We find that for no AGN, the infrared to mid-infrared ratio is of the order of 100-1000, while in agent sphere it is only 10. This mid-infrared to far-infrared excess in agent sphere is an indication of AGN activity, and therefore this suggests a synergy between far-infrared observation, like with ALMA, and near-infrared to mid-infrared observation, like in the future with GWST, that can allow for the unveiled or faint and or dust-obscured AGN. Let me summarize the results. In this work, we performed the radiative transfer calculation of a redshift 6 quasar-host galaxy. We find an edge emerging system that is consistent with ALMA HST observations of quasar plus SMG companions, and we also suggest a strategy that would allow to the unveil of faint and Ordasov skewed AGN by following up with GWST galaxies already detected by ALMA. Thank you for listening, and goodbye.